Welcome to Study Loop.
The self-inductance of a toroidal solenoid is given by L, and L is equal to mu naught, the permeability of free space, times the number of turns, all squared, times the cross-sectional area of the coil, all divided by 2 pi r, where r is the radius. So we know these values, and hence we can calculate the self-inductance. So mu naught is 4 pi times 10 to the minus 7, and that's Tesla meter per ampere. So all these are in SI units. The number of turns is 500, and that's squared. The cross-sectional area is given as 6.25 times 10 to the minus 4, and that's square meters. So since we use SI units, we can suppress the units in this calculation. All over 2 pi times the radius of 0.04 meters. And hence we get the self-inductance to be 7.81 times 10 to the minus 4 henries. So that's the self-inductance in the solenoid. Next, we want to calculate the magnitude of the self-induced EMF. Well, we know that the EMF epsilon is equal to L times the rate of change of current, di dt. And we've calculated the value for L, which is 7.81 times 10 to the minus 4. We suppress the units again. And the current changes from 5 amperes, from 2 amperes to 5 amperes, in a time of 3 times 10 to the minus 3 seconds. And hence we get an induced EMF to be 0.781 volts. And finally, in what direction is the current and the EMF pointing? Well, the current I is decreasing. And so the induced EMF will be in the same direction as the current. And this direction is from A to B. So the induced EMF is pointing from A to B, which means that B is at a higher potential than A.